All right, we're going to pick up where the video left off last time in section 1.2 with example number 2. And in this example, we are actually being given a formula, all right, a general term. And we're asked to find first the 5 terms of the sequence, and then second, to decide if the sequence is arithmetic. Remember, arithmetic means it adds or subtracts something every single time. Or if it's geometric, which means it's multiplying or dividing every single time. Or if it's doing something else. So we're looking at part A first, the 5n plus 6. So the first thing we're going to do is we're going to find the general terms the first 5 terms for n equal 1, n equal to 2, all the way up to n equal to 5. So if n is equal to 1, it means I have 5 times 1 plus 6, and what do I get? 11. And then I have 5 times 2 plus 6, and what do I get? 16. And then I've got n equal to 3. Actually, let me move this up a little bit to give myself some space. So I have 5 times 3 plus 1, which gives me 21. Yep.
Why did we change to plus 1?
Because I totally am zooming in and zooming out, and I lost my number. Apologize. Thank you. Please hold me accountable, Kaylee. I appreciate it. Because it should be 6. And the answers was given for the 21 actually went with a 6, so thank you for that. We'll fix it. All right, n equal to 4. 5 times 4 plus 6 would be 26. And the last one we're asked to find, n equal to 5. Okay, so that's part I of this problem, right? And then it asks us to decide, is this arithmetic, geometric, or neither? What do you think? It is arithmetic. So if it's arithmetic, it means that you believe that it's adding or subtracting something every time. So what value is being, and we should say it in terms of adding, what value is being added every time to get from term to term? Yeah, it's 5. So we're adding plus 5, right? So this is arithmetic.
Another question.
Yeah.
So when I looked at that, I already assumed it was arithmetic just because of the formula. So would we know beforehand before even doing that?
You can. So this formula matches the formula that we created back in example 1, or that you saw created on the video. You're right. And I will say too, and I may have also said in the video, so I apologize if I did and I'm just repeating myself, but there is a formula in your book for how to do this. I'm not a big fan of like, hey, you should go memorize a whole bunch of formulas. I'd rather you know where the formula is coming from and make sense of it, and so I don't usually teach it that way. In fact, I never do on this. But there is a formula in your book. It has N's and D's in it in terms of figuring out what the common difference is. And when we're adding and subtracting things, it's fine. There's nothing wrong with it. It's just, I don't think it's necessary. So, Kinsey?
Finding the sequence is from one answer to the next and doesn't really have to do with the formula, right? Does that make sense?
So finding out if it's an arithmetic sequence, you can do that from the numbers, right?
Yes.
Moving down these lists, yeah. Yes, you can. But as Mackenzie was saying, there is a reason that's happening, and the reason that's happening is because this formula looks like that pattern, where I have a number times n plus or minus another number. And that's how it always looks if it's arithmetic.
So if there's adding or subtracting something in the formula.
It's not the adding or subtracting that does it in the formula. It's the fact that you have a linear term, like n, multiplied by a constant 5. That's what's creating it to be arithmetic, actually. Yeah. Let's do the pattern for the next one. n equal to 1, n equal to 2. So I have 1 squared minus 1. Don't everybody talk at once. What is 1 squared minus 1? It's 0. How about 2 squared minus 1? It's 3. How about 3 squared minus 1? 4 squared minus 1 is 15. And then the last one, 5 squared minus 1 is 24. Okay, so that's part I. Is it arithmetic, geometric, or neither?
Neither?
It's neither. So arithmetic would mean you're adding something every time. Are you? The same number?
No.
No. So to get from 0 to 3 would be adding 3, but then from 3 to 8 would be adding 5, right? So that nixes it out. Can't be arithmetic. Geometric means I'm multiplying. There's no way I'm multiplying 0 by anything and getting to 3,
Yeah.
right? Like that just, it fails so fast. It's crazy. So it is neither. I would like to show you something interesting with this one, though. This is a good example to look at it from, because it's going to come up in your work where you're going to be given like a list of numbers, and you're going to be asked to figure out what comes next. But it's not quite so obvious what the pattern is to be able to establish. So I want to show you this. I'll pull it at the very end. So right now these numbers are 0, 3, 8, was it 15, and then 21? Those were them. Okay, so
24. Right? 24.
24, thank you. Be much more helpful to have that. Okay, so we said that it's not arithmetic, but this would be plus 3 if we were trying to do it that way. And this would be plus 5. Is there a pattern?
It goes up too.
Yeah, so if I wanted to find what comes after 24, could I do that without that formula on the previous slide? Yeah, I could do that. If this is how the problem began, I could find the next term. And if I didn't see it here, I could do it one more time. So check this out. How do you get from 3 to 5? 5 to 7? 7 to 9? If you go down far enough, there's some level of it that eventually becomes arithmetic. That's what's happening here. So even if you didn't see a pattern at the level 1, which we did, I mean, right, I get that. Just do it one more layer deeper and see if you can see it at level 2. And if you can't see it there, do it one more level deeper and see if you can see it at level 3. There will be a pattern that will emerge. In part because this is the kind of problems we're working with, is to establish that you can find patterns, right? Like this doesn't happen in every pattern you're going to experience in your whole life. I get that. But when you're looking for pattern, recognition of things, this will happen commonly. So we could actually find the next one, right? It should be plus 11. And if I add that, I should be at 35. And sure enough, that's right. Because what is 6 squared minus 1? 35. That's what the formula was that we did have on the previous slide. So I want to sort of have you see that there's this other way of thinking about patterns too that goes a step beyond just arithmetic, geometric, neither. And there are some examples in your book that have you do that in your homework. One more back. Inductive or deductive? Is this inductive reasoning or deductive reasoning? Let's jump back real quick to the definition since it's been a minute. Yeah. Oops, it was right there. Inductive reasoning is a method of making generalizations based on observations or patterns. Deductive reasoning is the use of mathematical axioms, theorems, definitions, or undefined terms assumed to be true and logic for proof. It's not inductive. So inductive is the one that we had last time. We were given a pattern and we made a generalization. What comes next? Is this, is this? What's the general pattern going on? We created a formula. Okay, so this one was actually inductive. Deductive happens when we're given a formula and then we're making claims after the formula has been given. So this one is deductive reasoning. Okay. Finding a counterexample for the following. So a counterexample, again, it's defined earlier, but I'll remind you here now, is an example that shows something's false. It's counter to what the example was supposed to be doing, right? If you're trying to prove something is false, you're finding a counterexample. So student does work like this, This would not be an uncommon thing for a student to do. They take n plus 5, they divide by 5, and they get n plus 1. So the first question here asks you to find a counterexample, an example showing that this process, whatever happened, it isn't right. We'll talk about what happened in a minute, but we need to create an example. So what does that mean? Well, it means I need to pick an n and find out that it doesn't work. And if you happen to pick an n and it does work, you just got to pick it again. Because they've told you it's not going to work, right? They've said find a counterexample. This one didn't say, does it work? Prove it with a counterexample or disprove it with a counter. That it doesn't ask you that way. It tells you it's not going to work by the very use of them telling you to find a counterexample. So what n would you like to try? 5. Awesome. Okay. So if we choose 5, I have 5 plus 5 over 5 on the left. And on the right, I have 5 plus 1. So what is 5 plus 5? 10. And what is 10 over 5? 2. So the left-hand side is 2. What is 5 plus 1? And 2 does not equal 6. Counterexamples for this one come easily. That doesn't always happen. Sometimes you try something and it actually works. So this is a counterexample. N equal 5 shows that this statement, again, whatever happened, doesn't work. So it's a good way to show a student that the mistake's not going to actually yield them what they thought, right? These two things aren't really equal. So any idea, speculation-wise, what you think a student might be doing to think that n plus 5 over 5 is equal to n plus 1? I mean, they might have tried a specific number and gotten it to work. It does, but that's not what the question's quite asking. The question is asking what operation did the student do? What did they think they could do to take what's on the left and make it become what's on the right? So it's almost like work you're analyzing in the students. This is what it started out with, and this is what the student said it equaled. What'd they do?
They might have thought that like the 5s would cancel out.
Yeah, I think you're right, Kaylee. And I think that's the most reasonable kind of assumption. So they are likely, and I'm going to use the word you did because that's the word they'd use too, canceling the 5s. Canceling is a really dangerous word. Just going to throw that out there, and we're probably going to all use it at some point. The reason it's dangerous is because we cancel things sometimes and turn them into zeros, and we cancel things sometimes and we turn them into 1s. It's kind of a scary term because what does it mean to cancel? So it's a better description to say that they reduced it, but likely they literally did this and canceled it, right? And not only that, but they could have just as likely gotten the answer of n as the answer n plus 1 from doing so, because when we cancel, sometimes things become zeros and sometimes things become 1s. Why didn't it work? Why can't I just mark the 5s out like that? Because I definitely can't. We got an example on part A that says we can't. We got a plus 1 on the other side, but that's not why that doesn't work.
Because there's an n plus 5.
Yeah, and what's going on with the n? It's also divided by 5, right?
Yes.
This whole thing is supposed to be divided by 5. So is there a way to rewrite it? There is. You could separate it out like this if you wish, and make each piece divided by 5. There's where that 1's coming from, right? This piece is equal to the 1. But the over 5 would still be applied to the n if we tried to do that. So n plus 5 is all, or you could say both pieces are divided by 5. And that's the reason we can't do it, is because we're just dividing one of the pieces by 5 if we do that sort of a marking out with the red, like I did, procedure. Okay, let's take a look at figure it numbers. Figure it numbers do show up, and they like to show up on like standardized tests. I don't know why. So your kids in your classrooms will likely see this at some level on standardized tests, and probably far before you would have expected them to see it. We're going to do a few things with it, but one of them is definitely the kinds of things you would expect to see on a test. So these are based on visually geometric patterns. These examples are neither arithmetic nor geometric, but the numbers can be represented by dots arranged in the shape of certain geometric figures. So I'm going to show you two sets of figure-it numbers. We're going to look at the triangular numbers, and then we'll look at square numbers. So the triangular numbers look something like this. Make sure my dot's big enough. You see that triangle shape showing up? If you don't want to draw it now, you can draw it later, but you'll want it in your notes at some point for it to make sense. These are 5 different sort of steps in our figure it number series. If we were to create a numerical pattern for this, that is, we were counting the number of dots. This one is 1, and then 3, and then what?
No, 5.
More. 6.
I was getting there.
It's okay. What's the next one?
10.
It's 10. And the last one?
50.
It's 15. So the kinds of things that you see, this is early elementary school stuff, not the numbers that I wrote, but the patterning, is where they write a pattern out and they say, what figure comes next? You've seen that before, right? I mean, like early elementary, like kindergarten stuff. They like to show patterns of things and ask what comes next in recognizing patterns. I want to show you something interesting one more time about this particular number pattern that shows up. And then we'll pause here and we'll finish this up next time. I've got 1, 3, 6, 10, 15. So I'm going to go to that ending slide again and write them out here since I have some more space. So I have 1, 3, 6, 10, 15. If I were looking for an arithmetic pattern here, right, what do I add each time? What do I add to get from 1 to 3? 3 to 6? 6 to 10? 10 to 15? Okay. Now, from the standpoint of my picture, that should make sense. Can you see how it's just adding this layer onto the bottom? It's almost like it shifts it up and adds another layer. And every time you do that, the next layer is just one more. So this bottom layer is 2, and this bottom layer is 3, and this bottom layer is 4, this bottom layer is 5. The next one's going to have a bottom layer of 6. All right, so it is adding 6 more dots to the bottom of the picture, and then we add 7 more dots, and then we add 8 more dots. From the number pattern, we can see it happening as well, right? We added it. Do you see what should happen next from the number pattern?
Yes.
Of course. We can do one more, and we're doing plus 6, and we'd have 21. Not only that, but take it one step further like we did on the problem right above this. And what do you get from 2 to 3? 1. 3 to 4? 1. 4 to 5? 1. So at this point right here, this happened to create another arithmetic sequence, right? At some point, I ended up getting the plus 1, plus 1. They all matched. Just like on the one above, I ended up getting the plus 2, plus 2, plus 2, and they all matched. So when this happens on the second time you do it, which is what happened both of these, it's actually called a common second difference. It's not a common difference. The differences were not in common, right? The first one was 3 and 5 and 7 and 9. Those were not common differences, but they have a common second difference. That is, if you do them a second time. Okay, so I'm going to pause the video here.